All right, thank you for joining online for today's lecture. So I have posted the syllabus online. You can check it out, especially if you are interested in doing the survey paper based on the book I posted. Please try to sign up as soon as possible to choose the chapters you want to cover because it's first come, first serve. And I know someone has already chosen a chapter. So basically try to sign up using the Google Sheet. But you don't have to cover the book. You can choose other papers you are interested in writing about. So you have the flexibility. And so for the, let me see. Yeah, so for the office hour, I will just try to be flexible. I will stay longer after each class to answer your question. But if that doesn't work for you, just try to email me and schedule an appointment for some separate office hour. That's the plan for this quarter. And one more thing is, as I mentioned last time, I will try to make this class more flexible and interactive. So therefore, I would encourage you to watch recordings from the previous year, I would say, and then try to come to the class with your questions. Hopefully we can make it more engaging. So that's what I want to do for today, because I suggested that you watch lectures 1 and 2 before this class, and I will try to cover some of the most important aspects I think I can have in mind and answer your questions. That's the plan for today. So just to get started, today we will talk about linear models, multiple linear models following our first lecture. And we will still focus on the inference of model parameters. So before we get started, I want to ask first, do you have any questions you want to specifically ask? You may unmute yourself or type in the chat box. Okay, I haven't received any responses. Then I will just go over whatever I think is important. All right, so just as a very quick recap, and to be consistent with the M by P notation for the design matrix, a question we got asked last time. So I'll try to stick with the M by P. So basically, for now, we're talking about this multiple linear model. In the matrix form, where Y is the outcome for n observations. And we assume that each yi is continuous. So we haven't talked about other types of yi yet. And we have a design matrix. X. And now let's just call it M by P. Last time we used P plus 1 because we consider P predictors one intercept, but let's make it M by P for simplicity. So this design matrix is assumed to be fixed in this class. And last time we gave the rationale because we're interested in the conditional relationship of Y given X. So basically, we tend to think that the distribution of X is unrelated to the distribution of Y given X. So that's why we focus on this relationship of Y given X, and that makes us not care about marginal distribution of X. That's the basic rationale. But in econometrics, there are people who try to consider the distribution of X and call that the random design problem. So for this fixed design problem, it's simpler because we only have the sources of randomness coming from the error term, not the design matrix. Then we typically have the first column as ones to denote the effect of the intercept. So it's the same effect applied to every observation. So we have a constant 1 in the first column. And then we have P minus 1 predictors. So typically we denote as xi1, I for the x1, 1 for the first observation to x1, P minus 1. So this first index for the observation, second index for the predictor. So that's the typical setting in statistics. We have rows as observations and columns as predictors or covariates or features, whatever you call it. Okay, then for the ith row, it's xi1 to xi p minus 1. And for the last row, it's xn1 to xn p minus 1. That's the setting. And we have an error term. Error vector, we call it epsilon. Same dimension as y. Epsilon 1 to epsilon m. So in this case, the sources of randomness only come from the error. So therefore, the assumption, any distribution assumptions we want to place is on epsilon. So the common assumption, we can go from the less restricted to the more restricted, right? The less restricted one is just to assume the epsilon i's are independent and each epsilon I has mean zero. This is the less restricted assumption. But if we want to go to more restricted, so more restricted is that you assume more, is that we assume epsilon i's to be IID following normal distribution, mean zero, same variance, sigma squared. So this is a stronger assumption. And the assumption that epsilon i's have the same variance is called, there's a jargon, this is called homoscedasticity. Very long term, many syllables, but it basically refers to this constant variance assumption for all the epsilon i's. Okay, so because of this, we can write a linear model in the matrix form, which is much simpler than the per observation model, right? We can write it for each xi, yi. That's complicated, actually. You have to write many terms. But the linear algebra make the matrix form simpler. It's just y equals x beta plus epsilon. Okay, so again, it's matrix. So n by 1, n by p, p by 1, n by 1. And the parameters of our interest is beta. Even though we also need to consider this sigma square, if we under this most restrictive form, we need to have the parameters, which is typically denoted as theta in statistics, as beta sigma square. So it's basically p plus 1 dimensions. But we need to be, and sometimes we put this transpose here to indicate this is a row vector. So probably I should put p beta transpose to make it row, then add one more element. So basically, we need to estimate beta, right? That's the key thing. And last time, what we talked about are two forms of estimates for beta, one based on least square or ordinary least square, which is short as LS or OLS, or maximum likelihood estimation. So as a very quick review, least square estimation does not rely on the distributional assumption of epsilons, but MLE relies on this normal assumption. But when MLE is under the normal assumption, it coincides with the least square. You have the same form. So basically, we have beta hat LS, least square, equals to beta hat MLE under the normality homoscedasticity assumption as X transpose X inverse X transpose Y. So this is just what we estimate, right? And we said that it's a linear combination of Y1 to Yn for each element of beta estimate. Because beta LS and beta MLE are both p-dimensional, containing our estimates for the p parameters. First one is our estimated intercept, then the coefficients of the predictors. So basically, beta, just try to write it out. Beta is beta 0 for the intercept, beta 1 to beta p minus 1 for the p minus 1 slopes. And then similarly, beta hat would be beta hat 0 to beta hat 1 to beta hat p minus 1. So this is something I want everyone to be careful about, especially if you are not if you are majoring in other disciplines, not in statistics, because I have seen many papers in which people just don't distinguish beta and beta hat. So they use the notation for the parameter and the estimator without distinction, and that would cause confusion. So that's something I want everybody to be very clear about. The way to think about it is for the parameter, it's what you assume in mind, but you don't know its value. But for the estimator, it's a transformation. It's a function of your data, of your x1 to, so the data, try to write it again, is this, which I wrote last time, xi, yi, I from 1 to n. Okay, that's the data. So basically in this setting, our xi is p minus 1 dimensional, containing the p minus 1 predictors. Yi is one-dimensional scalar. Okay, so given the data, your estimate is a function of your data. So it's basically some function of x1, y1 to xn, yn, but you cannot write that for beta. Beta is just the unknown parameter. That's the key difference. Okay, and this is the estimator, and we call this, in statistics, we call this point estimate. Because you just compute it based on your data, right? Put this into a design matrix X and put it into the outcome vector Y. You do the linear algebra, then you get the beta hat. So it's a point estimate. You get one value for each beta something, beta J. But it doesn't provide any uncertainty estimate. How sure we are, how much confidence do we have for this beta hat as a good estimate for beta? That's a question we haven't addressed yet, right? So therefore, we always, in statistics, we always concerned about two things about an estimator, bias and variance. Last time we said for bias, we showed already beta hat LS is, or MLE is just beta. So it's unbiased. As long as we have this loose assumption, relaxed assumption, expectation of epsilon is 0. As long as we have this, then we have the unbiasedness, which is good. And for the variance, we need this constant variance thing for the epsilon I and the fact that epsilon i's are independent. So we need that. So we need the constant variance at sigma square and independence of epsilon I, but we don't need the normal distribution form to get the variance of beta hat, or I should say variance covariance matrix. So it's a P by P matrix. And for this, last time we already showed it's X transpose X inverse sigma squared. So I'm just writing down the result. But for this one, we should bear in mind that it's not directly computable because we don't observe sigma square. So in practice, we plug in sigma square by an estimator. So therefore, what we are using is actually the estimator of the variance covariance matrix, which is that. And regarding this plug-in term, how do we compute it, right? So last time we said it's based on the residuals. And the residuals are different from the error terms. I'm trying to emphasize that again, because the residuals are based on our data and our model fitting, while the error terms are not depending on data. It's just something we have, again, in mind as beta. So therefore, what we have is sigma square hat. If it's MLE, okay, we can show that it's equal to, it's defined as EI square, square of the residuals and then average. And what is EI? So basically, E, residual vector, maybe I'll just write it, residual vector, E is a vector, right? and it's E1 to EM. And it's defined as Y minus Y hat. Okay, so Y hat is based on the fitted predicted value. Y is the outcome we observe. So coming back here, one thing we haven't said today, but we said it last time, is that given your parameter estimate, your Y hat is just defined as X beta hat, right? So therefore, given the formula for beta hat, Y hat is just X times X transpose X inverse X transpose Y. And we give this part before Y a name, called a hat matrix. So Y hat is just H times Y. So therefore, the residuals are naturally indicator n-dimensional minus hat matrix times Y. That's the residual. And then last time we said that the MLE estimator is biased because its expectation is not sigma square. So expectation of sigma hat square hat MLE is not sigma square. Instead, it's n minus p over n times sigma square. So we have this finite sample bias. So when n is very, very large, like n is much bigger than p, it doesn't matter. The bias is going down to 0. But when n is not so much bigger than p, then you will have this ratio, which is less than 1. Then that will cause the bias. So therefore, for the unbiased estimator, should be defined sigma hat. The unbiased version should be defined as 1 over n minus p instead of 1 over n minus 1 over n times this EI square sum. So this is just a generalization of the unbiased estimator for variance. If you just want to use sample variance to estimate the variance, you should divide by n minus 1 instead of n. Similar idea here. And this is also reflected, or we call this degrees of freedom, meaning that you loses p degrees of freedom because of your model here has p parameters to tie your n observations together. So this constraint will make your E1 to EM, your residuals, not as free as your error terms, epsilon 1 to epsilon m, because epsilon 1 and epsilon n are independent. So each one's value doesn't affect others' values. So that's why the degrees of freedom there is n. But here, E1 to EM, when you calculate them, you use the n data points together. So you actually tie them using p parameters in the high level sense. Then basically you lose this p degrees of freedom, and that's the price you pay using your model. So residuals are not error terms. Again, we should be clear about that. All right, so therefore, when we estimate the variance of beta hat, the sigma square we use in most statistical softwares, such as R and Stata, you are using the unbiased version to plug in. Okay, so I don't know if you have any questions so far. We talk about beta hat and we talk about the estimated variance of beta hat. However, knowing the mean of beta hat as the true beta, knowing the variance estimate in this form, still is not a full picture yet. We haven't talked about the distribution of beta hat around the true beta. What is the form of the distribution, right? Because having the same variance, the distribution could be very different. Like how concentrated is my beta hat on beta? That's another question. So for this, we would call this asymptotic distribution of beta hat. asymptotic distribution of beta hat. By asymptotic, which is a common term used in statistics, we actually mean that n goes to infinity. Okay, and in this class, because we're talking about the classical regression setting, we fix P. So you can see in this setting, when P is considered to be fixed, you're not getting more predictors as your sample size get large. Otherwise, that's called high dimensional statistics, which is not the topic of this class. You just let your observation go to infinity. So in statistics, we regard the data points or the observations as our resource. So the more data we have, the more information we have to learn. We can learn about the population. We can do inference better. That's the statistical logic. But I recently learned another interesting orthogonal view I can share with you, which I found very, very interesting myself. That is, people in computer science may regard the sample size n or number of data points as a burden, because if you care about computational complexity, then the larger n will make your algorithm run more slowly. So it's a very interesting difference, right? Because in statistics, we think the data are valuable, but that's also our shortcoming. Because if you ignore the computational complexity, your method may be theoretically justified, but you cannot implement it, right? If the method runs too slow on large data set, people will not use it. So the practicality is suffered. So therefore, it's always a balance, right? We need to think about nice properties if we have many data. But on the other hand, we need to know how to make the algorithm implementable. Anyway, so I think it's an interesting orthogonal thinking, similar to, in the same flavor to the Bayesian versus frequentist. So for the asymptotic distribution, still, even though this is not the focus of this class, because I had another class last quarter just to focus on asymptotics. So for this class, we'll not derive it, but we'll give you the result. The core for this whole derivation is central limit theorem, which we can say is probably the core for most asymptotic results used in statistics. Central limit theorem is about how the sample mean is distributed around the population mean, like xn bar is around mu. Here, we're talking about how beta hat is distributed around beta. And I can say that the result is just this. So basically, we have this beta hat and, or maybe I can give you I'll just give you the rough version of it. So beta hat is approximately asymptotically approaching to this distribution normal. And here is p-dimensional normal distribution. It's not one-dimensional because we're looking at the p elements of beta hat jointly. Mean beta and the variance covariance matrix is what we have over here, this one. So, okay. This is the asymptotic distribution. And again, because this is unknown, sigma square is unknown, in practice, we are using sigma hat square to plug in. And based on this, you could actually say, oh, because this is a p-dimensional distribution Gaussian, then every dimension of beta hat, so we will say beta hat j, right? Beta hat j for the jth element, it's approximately normal, one-dimensional normal, with mean as beta j. And the variance for beta hat j is just the jth element of this matrix. It's a jth diagonal element of this matrix. That will become its variance. Okay, so this would allow us a way to basically do inference for beta j directly. That means if we are interested in knowing whether this beta j is 0 or not, then we are in a hypothesis testing setting. So the hypothesis test would be again, like I said, we are just under frequentist, right? So everything we said in this class is under the frequentist paradigm. So that is a null hypothesis is we call the null H0, or people say H0, is beta J is 0, versus the alternative H1 is beta J not equal to 0. So what does this mean? If this beta J is the slope of the jth predictor, you are interested in whether the jth covariate has any associations with my outcome. And of course, one thing we have to be clear about, and we'll revisit this when we talk about ANOVA, is that this is conditional on other covariates. So when you talk about beta J, you are in this model. So let me just write it down again. You are in this model that yi for one observation is beta 0 plus xi1 beta 1 plus xi p minus 1 beta p minus 1 plus epsilon. So you're in this model. So when you talk about beta j, for example, j being 1 beta 1, then you are talking about the effect of this first predictor in the presence of other predictors. It's not just the predictor alone. That's very different. So basically, it's not as if I just write yi being beta 0 prime. I'm just trying to differentiate the two models plus xi1 beta 1 prime. I only include this only one predictor plus epsilon I prime. Okay, so for these two models, the beta 1 and beta 1 prime are not the same thing. And this is very important to know. Okay, so now let's just talk about this model where we have p minus 1 predictors. Then to test this hypothesis, I assume that many of you have basic mathematical statistics. So you are familiar with hypothesis testing. So you know there are several elements we need, I think 4 elements we need for a hypothesis test. First, hypothesis, null hypothesis, alternative hypothesis. You need to set it up. Second, test statistic. What would you use as a test statistic? And in this case, a natural choice of a test statistic is to use an estimator of beta j. So the test statistic should naturally start from beta hat j. But we know that for different beta hat j, the variance is different. So in the old days, without computers, we need to have some standardized distributions to make it into tables. Then we can look at the table to say, oh, this is the quantile for this distribution with this tail probability. People need to make up those tables. So therefore, with the distribution, right, once we have test statistic, the third element is the null distribution of the test statistic. That is, what would the test statistic be distributed like under the null hypothesis? So we don't want to have the null distribution to be too diverse in the pre-computer age. Then we cannot make up tables for so many distributions. But now, I should say, with computer, this is no longer a problem. You could, for sure, using just beta hat j as your test statistic and say, okay, this is the distribution. This is the distribution. I have it. Then under the null, this beta hat j would be normal with mean 0 and this variance. That's null distribution. Even though the variance term is specific to the jth element, but it doesn't matter. We can just do it computationally. So now it's not a problem. But in the old days, we want some standard null distribution. Therefore, we standardize beta hat j to a test statistic. And what we actually did is to divide it by the so-called standard error of the distribution of beta hat j. So it's the square root of the estimated variance of beta hat j. We call this term, so this denominator, we call it standard error instead of standard deviation. And I think the key difference, again, it's a jargon thing. I think the difference is because here for standard deviation, we mean it's the square root of the variance. But here we are not using the actual variance. We're using an estimated variance. So I think that's why people call it standard error. But anyway, again, it's a jargon. So we just standardize beta hat J, the estimate, by its standard error. Hopefully, its distribution doesn't rely on additional parameters, so we can make up standard tables. So in fact, this is defined as T statistic. Okay, so you can call it the T statistic. And the name comes from T distribution. So people can actually show that for this T statistic, its distribution under this assumption, that is, it follows this normal distribution. So beta hat J is normal. And when we plug in sigma square hat, which we can trace back to here, subject to some multiplier. So basically, this is that we can actually say that by multiplying n minus p to the left-hand side, then this term, sum of ei squared. Last time we said it follows chi-square distribution with n minus p degrees of freedom. And that is because of, and also I should say subject to some division for sigma squared. So just try to write it down. This one as a reminder. This follows chi-square n by p, n minus p. So this is a result of the normality assumption for epsilon I squared. But again, the normality assumption can actually be kind of relaxed when n is large because of central limit theorem, which can give us some very nice normality to play with. So let's just say that it's either n being large, so we can apply central limit theorem, or we make that epsilon I be normally distributed when n is small. So when n is small, we just assume more, we assume the normal distribution. Either way, we can have beta hat J normal, and this term chi-square together, we will be able to show that this follows T distribution, and the degrees of freedom is n by p. So again, as a recap of the derivation of T distribution, it is a manually constructed distribution by old day statisticians, the pioneers, because for convenience, we need to make up tables. And the definition of T distribution, which I introduced when I taught the Stats 100B, the undergraduate introduction to mathematical statistics, we spent quite some time to derive the T distribution. So in that case, in that class, we said the T distribution is considered to be two things. So the numerator, basically, numerator must be standard normal, random variable, and the denominator must be a chi-square random variable with certain degrees of freedom divided by that degrees of freedom. When this happens, then this ratio is defined to be T distribution with that degrees of freedom as the denominator. So that's the definition of T distribution. And we can actually show that basically, sorry, I should say square root. I forgot a square root. So we can basically show that this term, T statistic here, satisfies this. So inside the square root, we can show that this variance term, subject to some constant division, is a chi-square divided by degrees of freedom. And this numerator is also subject to some division for variance, is a normal, standard normal. So basically the constant here, numerator, and the constant from the denominator, they can cancel each other. So that's why we can have a form like this. So we can show its T distribution. So this is just a very, very brief recap of why it's the T distribution. But in practice, using the T distribution, we could just derive p-value for this test. So basically, t-distribution is under the assumption, I should say, beta J0, under the null distribution. We have the t-distribution. Then from this, we can get a p-value. And it's just based on the value, the observed value for the t-distribution based on our data, right? We're putting our data to compute beta hat j and this denominator. Then we get a value for t-distribution, for t-statistic. We put that value into the t-distribution to get the two tail probabilities, add them up, that's the p-value. So just in short, this is the T n minus P density. Let's say your observed value, T lies here. Then what we actually do is that we take the T and minus T by symmetry, and we take the two tails. It's a two-sided test, and they add up to give us the p-value. So that's how we get a p-value, based on which we can decide whether we reject the null hypothesis or we do not reject the null hypothesis, given a significance level, say 0.05. So that's the whole idea of inference for one particular beta j. And it's probably the most commonly used way to assess the effect of one predictor. But beyond that, as this is a graduate level class, we would need to consider multivariate, right? What happens if we're interested in more than just one predictor's effect? Oh, and one more thing, sorry, I should say that, I skipped that. One more thing, which is, I think, worth noting, is that in the definition of t-distribution, important thing is that the numerator's normal variable and the denominator's chi-square variable, they must be independent. That the independence is a key. Otherwise, you wouldn't have t-distribution. So for the independence here, this is a notation for independence. We need to check this for here. And you know, here the randomness of beta hat j comes from what? Comes from, going back to the formula here, beta hat is from here. This is beta hat, this form. And the randomness in the denominator comes from the residuals, right? Because we need the residuals to give us the sigma hat square. That's what we have for the variance estimate. So therefore, to satisfy this independence, we need to show that beta hat, we can show that as a sufficient condition, that is beta hat and the residual vector. This is p-dimensional, this is n-dimensional, they are independent. So we need to check this to make sure that we have the t-distribution. And there's a question in the chat box. And I think for, if you want to pose your question, please post it to everyone so everyone can see, not just direct message to me. And the question is it t-statistic solely because of plug-in estimation of sigma square? If sigma square were known, we could just use a z-test in that case. That's exactly right. Yeah, if you know sigma square, denominator becomes known, then you only have randomness in the numerator, which is normal distribution, then you can do a z-test. That's completely right. But this is only possible in theory, right? In practice, you would never know sigma square unless you're doing simulation. But for real data, you will never have that. Okay, I hope that answered the question. And back to the independence, to check this, which I think is very fun to show, because we know this, all right, again, normality really helps. Because beta hat is x transpose x inverse x transpose y, okay? And y, we know it's I minus h times y. So they're both linear combinations of y. And we know that y is multivariate normal. So this is n-dimensional multivariate normal, x transpose beta, right? And sigma square. identity matrix. This is like normal distribution for Y. So these two are also multivariate normal. So to check the independence between two multivariate normal random vectors, we just need to check their covariance being 0. So this is something special for normal. For normal, independence is equivalent to covariance, to 0 covariance. But this is not in general. In general, covariance being 0 doesn't imply independence. And this is something we should be careful about. But since it's normal, then we can just check that covariance of beta hat and E is a 0 covariance matrix. But we should be careful that this is a P by N covariance matrix because beta hat is P-dimensional, E is N-dimensional. So to check that, we'll go back to using the fact that, okay, beta hat takes this form, E takes this form. Then together, we can have a very nice cancellation when we calculate the covariance, and we can show that it's 0. And this is because of the form of H. Yeah, that gave us a nice form. But I would say this very nice coincidence we have this independence. I think it's a very interesting result to know. So I will skip the derivation because it's in the previous lecture recording. I'll just skip that. Okay, so this is for one test, for testing one coefficient. What if we're interested in testing whether multiple predictors coefficients are jointly 0? So if we move on to the multivariate version, and we can maybe divide our beta vector p-dimensional into 2 chunks. We call subvectors beta 1, beta 2. The first chunk is p1 dimensional, second chunk p2 dimensional with p1 plus p2 being added up to p. So in this case, if our null hypothesis becomes this vector null, which is beta 2 being 0, and this is a 0 vector with p2 dimensions, versus beta 2 is not a 0 vector. So this is known as I think it's called the composite null. Basically, you are having multiple equations. It's like every element in beta 2 is 0. Yeah. So in this case, how can we test that? So first question I want everybody to think is, why do we need to test such a null? Why is it different? Why cannot we just test P2 null hypothesis jointly? Sorry, let me pick up the. So you can consider just to be the test, the null hypothesis we're interested in, but it can be written as, right? It can be written as H0, or we can have like P2 H0 versus H1. You know what I mean? So you can decompose it into P2 tests and do that. I think I want to pose this as a question to engage you. Why do you think we want to do this joint test instead of testing P2 hypothesis and then aggregate?
Like multiple comparisons problem?
Yeah, when you have multiple tests, multiple p-values, then you will face another downstream issue, right? Afterward, after you do those P2 tests, how do you aggregate them? And then that will also be related to the estimates for these P2 elements in beta 2, how they are correlated. So you will have complexity like that. You cannot assume them to be independent because ultimately you can see that for the variance of beta hat, because this matrix, P by P matrix, is not necessarily a diagonal matrix. Therefore, you cannot simply say my beta J's are independent. So therefore, you will face that multiple testing issue. How do I aggregate? Which is a separate issue. So therefore, if you do this joint test, you don't face this multiple testing issue. You just jointly test this. And any correlation or dependencies among your beta hat J's can be accommodated. Okay, so I'll just say this has this multiple testing challenge. And I want everybody to be aware of this, even though we will not talk about multiple testing for now. All right, so if you don't need to do multiple testing, you don't have to. You can do it jointly. All right, but I would say in practice, which is kind of counterintuitive for statisticians from practitioners, is that people may prefer to do this one element test at a time, because they will probably think, okay, the results are easier to interpret than just joint test, because whenever I reject this null, right, I still don't know what elements of beta 0, beta 2 are non-zero. I still don't know what are the reasons why I reject this null. So that's why I think I face this complexity more and more as I understand both sides, what statisticians think, what practitioners think. For statisticians, of course, to avoid multiple testing challenge, let's do joint test. But for practitioners, the joint test result is not so informative because you don't know which elements are zero. So I think that's an open question I want everybody to think about. What strategy would you choose for your question? Anyway, let's talk about the joint test. For the joint test, then clearly the test statistic should be involving beta 2 hat, right? Beta 2 hat is a self P2 dimensional. Then how can we standardize this P2 hat, which is a vector, beta 2 hat, which is a vector, into a scalar value statistic? So one thing we should know is that for almost all the test statistics we use, they're scalar value. Then you can, with a scalar, you can have a one-dimensional non-distribution, then you can convert the test statistic into a p-value. But if the test statistic is multidimensional itself, then the p-value calculation is less straightforward. So therefore, the idea is similar to this standardization here, except that now we work with the vector instead of scalar. For scalar, we just standardize it by its standard error. But for the scalar, for the vector, we need something linear algebra. So this is known as the Wald statistic. And Wald was a pioneer or one of the early statisticians who has made very fundamental contributions. So just as a story, and many of you might have heard about this during the Second World War, there were he was involved in as a statistician for consultant. Then the question is about studying what are the vulnerable parts of the plane. So they used the planes that flew back, but with the bullets or shots in the body of the plane. The people thought, okay, these are where the plane have had wounds should be what we study. But he said we should study the other parts because of selection bias. Since the planes we have could return, that means the parts that were damaged were not the crucial parts. So he basically raised this very important point about selection bias or sampling bias. When we look at our data, we should think about whether the sample fully represents the population. Yeah, I think that's a very interesting story. But unfortunately, he died at a very early age due to airplane crash. So at that time, the airplanes were still not so safe. So his contribution for this is the Wald statistic. Because of that, the statistic is denoted by W. And the Wald statistic can be considered as the quadratic version of the T statistic. Because we need to work with vectors, we define it to be beta 2 hat transpose times the inverse of the estimated covariance matrix of beta 2 hat, which is P2 by BP2. We take the inverse times beta 2 hat. So this gives us a scalar because this is a row vector, 1 by P2, P2 by P2, and P2 by 1. Okay. And this Wald statistic has, if P2 is equal to 1, then this Wald statistic is just the square of the T statistic we introduced for one element. So again, we need to derive its null distribution. Okay, and again, I can give you the result under the H0, H0, W divided by P2, the dimension of beta hat 2, would follow an F distribution. And F is a distribution with 2 degrees of freedom called numerator degrees of freedom and denominator degrees of freedom is P2 and N by P, N minus P. P is the total number of parameters in beta. So beta 0, beta 1, beta P minus 1. So that's the P. And P2 is the vector we are interested in testing, the dimension of beta 2. And just like the T distribution is a manually derived distribution, so is the F distribution. The F distribution is constructed again for the convenience of making tables to look up. So the F distribution is defined as the ratio of 2 independent chi-square distribution. So basically for this kind of F, it's defined as the chi-square random variable with P2 degrees of freedom divided by P2, that's the numerator. Denominator is chi-square with N minus P degrees of freedom divided by N minus P. So for each chi-square random variable, we divide by its degrees of freedom. And again, we need to assume that they are independent. That's the construction of F distribution. Okay, and for this, you can actually think about this, even though we won't do the derivation here, but basically the intuition why Wald statistic follows this is because beta 2 hat is a multivariate normal distribution by either the normality assumption of epsilons or the central limit theorem when n is large. So each beta 2 has like a multivariate distribution, normal distribution, and the variance covariance of beta 2 hat would involve the sum of residual squares in the plugin part, right? In the plugin here, this plugin part. So that will give us some chi-square. So basically, when you have normal random variable square, you would introduce chi-square. And then you also have chi-square in this part. So together, you need some to work around with the formula here, but you will be getting a form like this, which follows F distribution. Okay, but in practice, people may say, okay, sometimes I will use chi-square distribution instead of F distribution, especially I know like if you do the linear regression in R, if you do Wald test, maybe you have a choice between the F distribution or the chi-square distribution. At least this is the case I know for the ANOVA, which we'll talk next time. For ANOVA, in R, you can specify the distribution you use for the p-value calculation. So what's the connection here? So maybe we should come back to the T distribution first, and then we talk about F distribution. They share many similarities. Just like if you think about the correspondence, T versus F is like normal distribution versus chi-square. So normal is for the unsquared version. T and normal are for unsquared. They could be positive or negative and symmetric about 0. While chi-square and F, they are only taking positive values. They cannot take negative values, and they are the squared version. So for T distribution, its relationship to normal is if I let my n go to infinity, asymptotically, this T distribution will converge to standard normal distribution. That's a known fact. And also, if you think about the shape, both T and normal have the bell shape, but T has heavier tails. So basically, given the same value here, the two tails will the two tails will have larger probabilities under T than normal. Normal has a light tail actually. So, but as your degrees of freedom for T goes to infinity, T is convergent to normal. Okay, this is for the factor T distribution. Then for F, what we have for F distribution is that if we multiply F distribution by the numerator degrees of freedom, okay, if we multiply P2 and this F, so we multiply this F random variable by the P2 degree of freedom, and we let the denominator degrees of freedom to go to infinity. So when we still let n go to infinity, this will converge to chi-square distribution with P2 degrees of freedom. So there's also correspondence here. So therefore, we have either W divided by P2 under the null follows F distribution, or I would say these two things are approximately the same, or we could have W under the null follows chi-square distribution with P2 degrees of freedom. Okay, so basically F converges to chi-square, T converges to normal, but for F, the trickier thing is that we should multiply F by the numerator degrees of freedom. So we say that in the setting of linear regression, we say that if you use normal distribution for the T statistic or chi-square distribution for the Wald statistic, we call that asymptotic null distribution. But if we use T distribution for T statistic and F distribution for Wald statistic, we call this finite sample null distribution, even though this still requires normality assumption for the error terms. So it all starts from there. Otherwise, if you don't have that normality assumption for error terms, you have to rely on central limit theorem, then it's basically asymptotic. You can only have the result work well when n is large. I hope this makes sense. Okay, any questions before we move on? Okay, so then let's continue. So an alternative for doing the same test for beta 2 being 0 versus beta 2 not being 0. And you know, this is the general version of the one element test, right? But for both the more specific one element test or this more general vector test, we can do it in another way by likelihood ratio test. So likelihood ratio test would rely on this normality assumption for epsilon I, because that's how we can write down the likelihood, which we actually did last time. We wrote on the board for the likelihood last time. And this time, we will just say that, okay, so how do we do the likelihood ratio test as an alternative? So I think this can also give you an idea that for the same question, we may have more than one statistical solutions to tackle the same problem. So I think that's why statistics is not like, how to say that? It's not like an automatic pipeline that people can just use, because there could be multiple choices and which one is more reasonable requires many justifications. It depends on data, depend on the question, and also depend on the knowledge of people who do the analysis. So that's why I feel like, even though maybe this is just like, I would say this is not specific to this course, but I think it's a general question. I think it's many people who know statistics, who especially those who got their PhDs in statistics, would like to develop new methodologies because that's how they are evaluated or they are appreciated. But on the other hand, we do need people to use statistics in many applications, many important applications. But if people who use statistical methods do not understand what's going on, there is a risk that the methods may be misused. So there's a gap between our training and the use of statistics. But in my opinion, I think we do need more people who understand statistics to participate in important applications so we can use the methods properly. And instead of just inventing more methods, because anyway, we need users, right? More methods will not clarify things. So coming back to the likelihood ratio test, it's a more general approach, as long as you can write down likelihood. Okay. Typically, I would say in the general setting, you basically, when you say likelihood ratio test, you're comparing the null hypothesis where you have a smaller model. So the model has more restrictions. Like basically, I would say you have more assumptions put into the model versus an alternative as a larger model, fewer constraints. And the two models must be nested. So the smaller model must be nested under the larger model. In other words, the smaller model is a special case of the larger model in which you set some parameters to certain values. So in this case, in our regression setting, we can say that when we set beta 2 to be 0, that's the smaller model because we arbitrarily set the P2 coefficients in beta to be 0, while under the alternative, we do not require beta 2 to be 0. They can take any values. So in a linear model setting, this is called a full model because we don't put any constraints on the parameters, coefficients, but this is a constraint, smaller model. So the likelihood ratio test statistic, by the name, right? It's constructed first to get a likelihood ratio denoted by the big lambda. This is the capitalized version of lambda, which is defined as likelihood ratio. So we take the likelihood of beta, maximize it under the null hypothesis. Under the null hypothesis, under the constraint, we find the maximum likelihood estimator. So in this case, we would just fit the model using our linear regression by setting beta 2 to 0. So then we only estimate the parameters in beta 1. And the denominator is the unconstrained one. We just maximize beta without the constraint. Then intuitively, which likelihood will be bigger? The second, the denominator, right? Because it has less constraint, we can make it larger. So therefore, we know this ratio is for sure less than 1, right? And also we know that we prefer to work with log likelihood instead of likelihood. The reason is because for many well-studied distributions, they're called exponential family distributions. I think I will probably, we will talk about that later in this class. Yes, we'll talk about exponential family. So Gaussian, Poisson, they belong to the distributions you are familiar with. They belong to exponential family. So it's a generalization of the common distributions. And for exponential family distributions, their density functions typically involve the exponential function. So that's why once you take the log, you make the log density and the log likelihood to not involve exponential function. That's why it's nice. So we work with log likelihood ratio, and we call it log lambda, right? So we know that for the log likelihood, we typically use the lowercase l instead of the uppercase L for likelihood. Then it's the max beta belonging to null, small l beta, minus the unconstrained max, small l beta. So that's the log likelihood ratio. And we know this is negative. And for most of our test statistics and their null distribution, the standard null distributions, they are positive. So that's why we need to add a negative sign to it. So that's why in most cases we work with the test statistic is actually -2 times log lambda. That's a test statistic we use for likelihood ratio test. And the -2 is there also for a reason, because of what? Let me tell you. The reason is that if you have the linear model with normality, so I just say it's the epsilon IID normal sigma square constant assumption. Under that assumption, this log likelihood ratio would take this special form, which is, I'll introduce the name first, and then I'll define it. RSS under H0 minus RSS for the full model divided by 2 times sigma square. And you see the 2. That's why we multiply by the 2, so we can cancel this 2 in the denominator. And this 2 sigma square actually comes from the Gaussian normal density function, if you remember. In the exponential function, in the exponential to the negative something, right? In the denominator of that exponent, it's 2 sigma square. And that's what it enters here. And this RSS is defined as residual square sum. So RSS is basically sum of the residual squares, the thing we have seen already. Okay, and later when we talk about ANOVA, you will get another name, SSE, and that's sum squared error. Even though I said multiple times we shouldn't call it error term, but people just call it by convention. So it should be residual, but it's residual sum square error. So you will see both terms and they refer to the same thing. It's just the sum of square residuals. And here, when we see RSS H0, it means the residuals were derived from this smaller constraint model. Or if we just say RSS, it's the residual we obtain by fitting the full model. That's it. And then you see that for this thing, right, we can see that it becomes, we just do the multiplication and we would get, sorry, I forgot the negative sign here. The negative sign is important. And you can easily see why it should be there, because under the constraint model, we have a smaller likelihood, but larger residuals, because the fitting is poorer, right, to the data. The more parameters, the better the fitting. So therefore, this RSS should be bigger under the constraint model than the full model. So we need this negative sign because we know this is negative, as we said. Anyway, so now we multiply -2 to make it positive. Then this term is just RSS H0 minus RSS divided by sigma square. Okay. Again, this is not a practical test statistic because sigma square is unknown. So we need plugging again. And here is an interesting question for you. Which one should we plug in? How do we plug in the sigma square? Recall that sigma square hat, the unbiased estimator we just talked about today, is RSS over M minus P. But now we have 2 models. The constraint model, smaller model under H0, the full model under H1. Under each model, we could have sigma square hat. I mean, the question is, so for the plugin here, should we use RSS H0 over, in that case, the degrees of freedom is M minus P1. Because we only have these parameters to estimate, right? The other P2 are set. or RSS over n minus p. Which one should we use to plug in for the sigma square in the likelihood ratio statistic? Any thoughts? We have 3 minutes.
Shouldn't you use the one under the null?
We should use the one under the null. Why do you think so?
I figure that's like part of hypothesis testing.
Okay, you thought because the test statistic, yeah. So your rationale is because the test statistic should be, we were concerning its distribution under the null, right? That's why you think we should go with the null. Yeah. Okay, I see some nods, so which means that many people agree with this. But unfortunately, in practice, we're using this. So we are using the full model for that. Actually, this is a question I got to ask every year, every time I taught this class. I think it's something interesting. It actually ultimately it relates to the fundamental challenge for statistics, which is the assumption of a true model, the belief of a true model. Which one do you believe to be the true model? That's the problem. So honestly, we have this nice result for chi-square distribution, this one divided by, again, right? This one divided by, just to write it again. N minus P. This result is the key to derive the asymptotic null distribution, but this one will rely on true model. And here, the true model is still assumed to be the full model. So that's why this holds. But if we use the constraint model, which is not a true model, we wouldn't have this following chi-square n minus P1. I think that's the fundamental reason for this mathematical derivation. It's about the belief. But on the practice, on a practical note, I know this may not be so convincing to practitioners who don't believe in true models. But anyway, I think the challenge is that if you want to do statistical inference, you must have some true model, some model in mind. Otherwise, the inference is a mission impossible. It's unlike prediction. For prediction, you don't need to have a true model. You just check the performance. But for inference, it's all about what we think in mind. So therefore, this is one justification about the true model thing. Another justification is practically using this, we would get, how to say that? I think using this, we would get a smaller sigma square hat, because as we know, using the full model, you will have smaller residuals, and then you have a smaller estimate for sigma square. Then you will have a bigger test statistic, right? You're dividing a smaller thing, and having a bigger test statistic, you would be more conservative. Or I shouldn't say more conservative. I think that's the wrong way to say it. Because having a bigger test statistic is actually the opposite of conservative. You are more likely to reject the null hypothesis. Yeah. Because if we're under the same null distribution, say chi-square, then having a bigger statistic, you'll have a smaller tail. So anyway, so basically the test statistic we use in practice, because this is the hypothetical one, right, with this unknown parameter. What we use in practice is this negative log lambda hat, which is RSS H0 minus RSS divided by RSS over n minus P. That's what we use. And asymptotic distribution, I would say under the null, the asymptotic distribution is chi-square with degrees of freedom P2. P2 is the difference in degrees of freedom between the smaller model and the bigger model. Since the smaller model specifies P2 parameters to be 0, so you lose your difference in degrees of freedom is P2. So I think this is something nice about likelihood ratio test, because the result is very easy to remember. You just have the negative log likelihood ratio, and then the asymptotic distribution. This is asymptotic distribution. It's just chi-square whose degrees of freedom is the difference in degrees of freedom. So it's very easy to memorize. But to apply it in practice, we need to have the two models nested. And also people should be quite careful about some boundary situation. By boundary, we mean that, okay, the parameter you specified under the parameter values you specify under the smaller model, if it's in the boundary of the parameters value domain. So the parameter can pick different values, but if you specify the value to be at the boundary, there could be some issues with asymptotics. So these are some cautionary messages. But in general, the likelihood ratio test is very useful for many applications. So yeah, I guess we should stop here. And hopefully you will have more time to watch the lecture for next Monday lecture. Then I hope you can come up with more questions. So it'll be more interactive next time. Yeah. All right. So thank you all for today. Hopefully I'll see you in person next Monday. Bye. And I'll stay here for longer in case you have any questions.